In this video, we're going to talk about cyclic groups. We introduced cyclic groups back in our video about groups of orders 1 through 3. Well, in this video, we're going to try to tie up some loose ends by talking about orders of elements in cyclic groups and their subgroup structure. First of all, let me remind you of the definition. A group G is called a cyclic group if all of the elements of the group can be written as powers of a single element little g. In this case, the element little g is called a generator for the cyclic group. I want to remind you, though, that this notation is assuming that g is written multiplicatively. If g is written additively, then instead of writing g to the k for the group generated by the element little g, we write this set as the set of multiples k times g where k runs through the integers. We've already seen this kind of distinction many times in our examples in previous videos, so hopefully you're getting comfortable with it by now. One thing which was mentioned back in the video where we first introduced cyclic groups is that two cyclic groups of the same order are always isomorphic. Now, I didn't stop to rigorously prove that, but it's pretty easy to show that if you have a cyclic group G generated by an element little g and a cyclic group H generated by an element little h, then the map tau from G to H, which sends every element of the form little g to the k to the element little h to the k, is a bijective homomorphism of groups, so it's an isomorphism. We haven't really said much about isomorphism beyond just the definition, but even with just the definition, it's pretty easy to check that this is true. Now, to collect together some other facts that we know, we've already established in previous videos that there's one cyclic group of order n for every natural number little n. Our notation for that group, which is unique up to isomorphism, is Cn, and a presentation for the group is the group generated by the element x subject to the relation x to the n is the identity. We've also seen an additive version of this group, which is the group Z mod nz. We know that this is also a cyclic group of order n with a binary operation of addition modulo n, and a generator for the group is the residue class 1. So Z mod nz is the additive counterpart of the multiplicatively written group Cn, but the two groups are isomorphic to each other because they're both cyclic groups of order n. Now, in addition to the cyclic groups of order n for all natural numbers n, there's also an infinite cyclic group, which is just the group generated by x with no relations whatsoever. An additive version of this group is the group of integers under addition, and a generator for this additive version of the group is the integer 1. When we're writing it with multiplicative notation, we may also write the infinite cyclic group as C sub infinity. The next thing that I'd like to talk about are orders of elements in cyclic groups, but before I do this, I'd like to remind you of a couple facts from our video on subgroups. First of all, just to make sure that we're all on the same page, I'd like to remind you of the definition of the order of an element of a group. So if capital G is any group and little g is any element of the group G, then the order of the element little g, which we're going to denote in this video by absolute value g, is defined to be the smallest positive integer k with the property that g to the k is the identity, or infinity if no such k exists. If you want to see more basic details about the definition, you can look back at the video on subgroups. The second thing that I'd like to remind you about from our subgroups video is a theorem which I'm going to call here Theorem 0. And what it said, first of all, is that for any element little g of any group capital G, the order of the element little g is the order of the cyclic subgroup that it generates. Now, I hope you remember that we actually proved this in our video on subgroups. And in fact, we proved an even more precise version of this statement, which has two parts. The first part says that if the order of the element little g is infinite, then all of the distinct powers of little g are different from each other. In other words, if the order of g is infinite, then g to the I is never equal to g to the j if I is not equal to j. This fact is going to help us when we're dealing with infinite cyclic groups. The second part of this theorem dealt with the case when the order of the element little g is finite. And what it said is if the order of g is little n for some natural number little n, then the subgroup generated by G consists precisely of the n distinct elements, g to the 0, which is the identity, g to the 1, g squared, all the way out to g to the n minus 1. Furthermore, for any integers I and j, g to the I is equal to g to the j if and only if the two exponents I and j are equal to each other modulo n. So this just tells us that when we take an element of order little n, and we start taking powers of it, they cycle around with period n through these n distinct values. Now let's talk about orders of elements in cyclic groups, and let's start with the case of an infinite cyclic group. So let's suppose that we have an infinite cyclic group with a generator x. Well, we know that every element of this group looks like x to the k for some integer k. And when we're talking about the orders of elements of the form x to the k, there are two cases to consider. The first case is when the exponent is 0, but in this case x to the 0 power is just the identity, and it follows straight from the definition of order of an element that the order of the identity element is 1. So that takes care of that case. Now we claim that when k is any integer besides 0, the order of the element x to the k in this group is actually infinite. And to see why that's true, let's argue by way of contradiction. So let's suppose that the order of x to the k is q for some natural number q. Well, of course, by the definition of order, that means that x to the k to the q power is the identity element. But by properties of exponents, x to the k to the q power is x to the kq power. And if x to the kq power is the identity, then it means that the order of the element x is less than or equal to k times q. But by theorem 0, since the order of an element is equal to the order of the group that it generates, that would then imply that the order of C infinity is finite, and that's clearly a contradiction. Therefore, we conclude that our original hypothesis was false, which leaves us with the conclusion that the order of x to the k is in fact infinite. That concludes this proof, and these two cases together give us the full story about orders of elements in infinite cyclic groups. Next, let's talk about orders of elements in finite cyclic groups, but before we do so, let's prove a lemma which is pretty useful in its own right. What the lemma says is that if G is any group, and if little g is any element of the group G, with order equal to n for some natural number n, then g to the m is the identity for some integer m, if and only if m is 0 modulo n. In other words, if g to the m is the identity for some integer m, then that integer m has to be divisible by n, and also if you have any integer m which is divisible by n, then g to the m is the identity. Now for the proof of this, let's suppose that little g is an element of a group G with order equal to little n for some natural number n, and let's prove that the right-hand side of this biconditional statement implies the left-hand side, and then that the left-hand side implies the right-hand side. For the first direction, let's suppose that m is an integer which is 0 modulo n. So what we want to prove is that g to the m is the identity. Well, if m is 0 modulo n, then it means that m is L times n for some integer L. But then by properties of exponentials we have that g to the m, which is g to the ln, can also be written as g to the n to the L power. Now since n is the order of the element g, we know that g to the n is the identity element, so the expression on the right-hand side is the identity element, and that's exactly what we wanted to show. That proves that the right-hand side implies the left-hand side. For the other part of this biconditional statement, let's assume that g to the m is the identity element, and use that to prove that m has to be 0 modulo n. We'll start by using a trick which we've seen a lot of times, which is to write the integer m as an integer q times n plus a remainder r which is bigger than or equal to 0 but less than n. Of course here I'm using the division algorithm to guarantee that integers q and r like this exist. Well, since g to the m is the identity element, I can substitute in m equals qn plus r, and then use properties of exponentials to write that as g to the n to the q power times g to the r. But since g to the n is the identity element, I know that g to the n to the q is the identity, so the left-hand side here is just g to the r. Well now, r is a non-negative integer which is strictly less than n and which has the property that g to the r is the identity. My assumption was that the order of the element little g was n, so there can't be a smaller positive power of g which is the identity, and that leaves me with the conclusion that r must be 0. That establishes the second half of this biconditional statement, so it finishes the proof of the lemma. Well, now we're ready to give a formula for the orders of all elements in a cyclic group of order n. If Cn is generated by the element x, then every element of this group looks like x to the k for some integer k, and the order of the element x to the k is given by the formula n divided by the GCD of k and n. Just as a reality check, remember that the GCD of k and n is a divisor of n, so that the quantity on the right-hand side is always a natural number. Well, for the proof of this, let's start by trying to understand the collection of all integers m with the property that x to the k to the power m is the identity element. Remember by the definition of the order of an element that the order of the element x to the k is then going to be the smallest positive element in this set, or infinity if no such element exists. Well, just by properties of exponents, this is the same as the set of m and z with the property that x to the power km is the identity. But now, using the lemma that we just proved, together with the fact that the order of the element x is n, we have that x to the power km is the identity element, if and only if k times m is 0 modulo n. Therefore, this set is the same as the set of all integers m with the property that k times m is 0 modulo n. Well, this set is definitely non-empty since, for example, m equals 0 is a solution to this equation. And in fact, we know from our video about integers modulo n that the set of all solutions m to this equation is precisely the set of all integers m with the property that m is equal to 0 modulo n divided by the GCD of k and n. That's something that we proved and went over in detail in that video, so you can look back at that to see how the proof goes and even to see some examples. Well, now we're basically done, because as we said before, the order of x to the k is the smallest positive integer in this set. Since any integer m which is 0 modulo n over the GCD of k and n must be a multiple of n over the GCD of k and n, the smallest positive integer in this set is n divided by the GCD of k and n. Therefore, that's the order of the element x to the k. Now, in some of our examples from previous videos, we noticed that cyclic groups can have more than one generator. So we might have asked, which elements of a cyclic group of order n are generators for the group, and how many different elements of this group are generators for the group? Well, we can answer that now, so let's suppose that Cn is generated by the single element x, so that by theorem 0, it consists of the elements identity x, x squared out to x to the n minus 1. Well, now we have a formula for the order of the element x to the k, and we know that it's n divided by the GCD of k and n. Since the order of the subgroup generated by x to the k is equal to the order of x to the k, this is going to be a generator for the whole group if and only if its order is equal to n, and that's only going to happen if the GCD of k and n is equal to 1. So Cn is going to be generated by x to the k if and only if the GCD of k and n is equal to 1. So what does that mean about the question of how many generators there are for this group? Well, these are all the distinct elements of the group, and to figure out which ones are generators, we just need to look at all of the exponents from 0 up to n minus 1 and count how many of those are relatively prime to n. Well, we've talked about this before, and the number of integers from 0 up to n minus 1 which are relatively prime to n is what we call the Euler phi function of n. So the answer here is that there are exactly phi of n generators for the cyclic group of order n. Now before we move on, let's take a look at a couple of examples. We'll look at one easy example and then a couple slightly more interesting. So for the easy example, let's take the cyclic group of order 15, which we'll write as the group generated by an element x, and let's ask which elements of this group are generators for the group. Well, to figure that out, we just go through all of the powers of x, which are relatively prime to 15, and in the end we find that there are exactly 8 generators. Now we can double check our answer by computing the Euler phi function of 15, which of course is 3 minus 1 times 5 minus 1, or 8. So that gives us some assurance that we found all of the generators here. Now for a more interesting example, let's suppose that n is p to the l for some odd prime number p and some natural number l. Well then, by the primitive root theorem, we know that the multiplicative group of primitive residue classes modulo n is a cyclic group. And we also know that the order of this cyclic group is phi of n, which in this case is p to the power l minus 1 times p minus 1. Well now, from what we've said about cyclic groups, we can deduce a couple of facts about primitive roots modulo n. The first fact is that when n is a power of an odd prime, the number of primitive roots modulo n is phi of the order of the group, which is phi of n, or phi of p to the l minus 1 times p minus 1. So this is the number of residue classes modulo n, which are generators for the multiplicative group of primitive residue classes modulo n. Now, once we've found one primitive root g modulo n, we can also use it to list out all of the other primitive roots modulo n. And that's because if g is a generator for this cyclic group, then the collection of all generators for the group is given by g to the k, where k runs through all of the residue classes modulo the order of the group, which are relatively prime to the order of the group. In this case, the order of the group is phi of n, so if g is a primitive root modulo n, then the collection of all primitive roots modulo n is precisely the collection of all residue classes g to the k, modulo n of course, where k runs through the integers from 1 to phi of n which are relatively prime to phi of n. In case it helps to see an example with numbers, in the previous video we computed that 5 is a primitive root modulo 103, and we can use that fact to list out all of the primitive roots modulo 103. Now first of all, 103 is an odd prime number, so the Euler phi function of 103 is just 102, and that's the order of the multiplicative group of primitive residue classes modulo 103. Well, to figure out how many primitive roots modulo 103 there are, I now need to compute phi of 103, or phi of 102, so I need to factor 102. 102 factors as 2 times 3 times 17, and from this it's easy to see that phi of 102 is 1 times 2 times 16, or 32. That means that there are exactly 32 residue classes modulo 103 which are primitive roots modulo 103, and if I want to list them out, then I can go through and compute 5 to the k modulo 103 for all integers k going from 1 up to 102 which are relatively prime to 102. Now, I don't really have any reason to do this computation, but you can see that in principle this gives you a way to compute all of the primitive roots modulo n once you know 1. Next, let's talk about subgroups of cyclic groups, and let's begin by proving an important theorem which we're going to call Theorem 1. What Theorem 1 says is that if G is a cyclic group generated by the element x, and if H is any subgroup of G, then either H is the trivial subgroup, or H is the group generated by an element of the form x to the k, where k is the smallest positive integer with the property that x to the k is an element of H. Now, in order to prove this theorem, let's suppose that H is not the trivial subgroup, so that what we want to prove is that the description in the second half of the theorem here holds. Well then, let's let S be the collection of all natural numbers L with the property that x to the L is an element of H. Actually, to start with, we should check to make sure that there is an integer k like in the description of the theorem here, but that's something that's going to be guaranteed for us by the well-ordering principle, if we can show that the set S is non-empty. Well, since H is not the trivial subgroup, there must be a non-zero integer L with the property that x to the L is an element of H. Now, if that non-zero integer L happens to be a positive integer, then right away we know that the set S is non-empty. But even if the integer L that we chose happens to be a negative integer, since H is a subgroup of G, we know that it's closed under inverses, so if x to the L is in H, then x to the minus L is also in H. And if L is negative, then minus L is positive. So either way we conclude that the set S is a non-empty subset of the natural numbers. Well then, by the well-ordering principle, we know that S has a smallest element, and that's the smallest element which we call k, as in the description of the theorem here. Now that we know that the positive integer k in the statement of this theorem exists, in the case when H is not the trivial subgroup, we want to show that H is the group generated by x to the k. And we'll do that by showing that the group generated by x to the k is a subset of H, and then by showing that H is a subset of the group generated by x to the k. The first inclusion is pretty easy, and it follows directly from the fact, mentioned in the video about subgroups, that the group generated by a set is the smallest subgroup which contains that set. Therefore, since x to the k is an element of H, the group generated by x to the k also has to be a subset of H. That proves one inclusion. Now, to prove the next inclusion, let's suppose that little h is an element of H. Well, since every element of H is an element of G, and since the group G is generated by the element x, we know that little h has to be of the form x to the L for some integer L. Let's write L as q times k plus r, using the division algorithm, so that r is a remainder which is bigger than or equal to 0 and less than k. Since we're trying to show that every element of H is an element of the group generated by x to the k, we want to show that L is actually a multiple of k, so we want to show that the remainder here is actually 0. Well, here the key is to multiply x to the L by x to the minus qk. And since the group generated by x to the k is a subset of H, we know that x to the minus qk is an element of H. Well, here I'm multiplying together two elements of H, and since subgroups are closed under multiplication, I know that I'm going to get another element of H. But when I multiply together x to the minus qk times x to the L, by properties of exponents, I'm just left with x to the r. Okay, but now k was chosen to be the smallest positive integer with the property that x to the k is an element of H. And I know that r is strictly less than k. Therefore, that forces r to be 0. And it allows me to conclude that the element H is actually x to the k to the power q, which is an element of the subgroup generated by x to the k. That gives me the reverse inclusion that H is a subset of the group generated by x to the k. And it allows me to conclude that these two groups are actually equal to each other, therefore completing the proof of Theorem 1. We're now ready to give a complete classification of the collection of all subgroups of an infinite cyclic group. So let's suppose that I have an infinite cyclic group generated by an element x. Well then, the collection of all subgroups of this cyclic group is the collection of all groups generated by elements of the form x to the k, where k goes from 0 to infinity, and furthermore every group in this list is distinct. So no two of these groups are the same. Now first of all, by the theorem that we just proved, we know that every subgroup of this group has the form group generated by x to the k for some non-negative integer k. So what we really want to focus on here is proving that any two subgroups in this list are distinct. Now let's suppose that I have two integers k and l with k less than l, and let's show that the subgroup generated by x to the k is not the same as the subgroup generated by x to the l. I'll break the argument here into two cases. So in the first case, if k is 0, then the group generated by x to the k is just the trivial subgroup, which is a group of element 1. But since L is strictly larger than k, the order of the element x to the L is infinite. But by theorem 0, the order of the element x to the L is the same as the order of the cyclic subgroup that it generates. So here I have an infinite group and a group of order 1, therefore these two groups are definitely not equal to each other. For the second case, let's suppose that k is bigger than 0. Well then, k is a positive integer which is strictly less than L, so it's definitely not equal to QL for any integer q. And again, by theorem 0, that guarantees that x to the k is never equal to x to the QL for any integer q. Well, that implies that the element x to the k is not an element of the group generated by x to the L, once again allowing me to conclude that these two groups are distinct. That completes our characterization of the collection of all subgroups of an infinite cyclic group. Now, one more thing that I want to point out about this before we move on is that it follows from this characterization that the only generators for the infinite cyclic group generated by x are the elements x and x inverse. Now, to see why that's true, let's suppose that the infinite cyclic group is generated by x to the L for some integer L. Well then, L certainly can't be 0, since then you would have the trivial group here, and whether L is positive or negative, C infinity is also going to be generated by x to the minus L. So we can always say in this case that it's generated by x to the absolute value of L, and we know that absolute value of L is a positive integer. Well, we already said that all of the groups in this list are distinct, and we know that C infinity is generated by x to the 1, therefore this allows us to conclude that the absolute value of L must be 1, which forces L to be plus or minus 1. So that verifies this claim that the only generators for the group are x and x inverse. Now let's talk about finite cyclic groups. Here the story is a little more interesting. So let's suppose that n is a natural number and that Cn is a multiplicatively written cyclic group with generator x. Then it turns out that there's exactly one subgroup of Cn of order d for every positive integer divisor d of n. Now I want to be even more precise about this, and so I'm going to break this statement down into three pieces. First of all, if h is any subgroup of Cn, then the order of h has to divide n. And if you watched the previous video, then you should already know the reason for that. Now secondly, and this is something which is kind of special about cyclic groups, for every positive divisor d of n, there is a subgroup of the cyclic group of order n which has order d. And it's pretty easy to see using properties of orders of elements in cyclic groups that the cyclic group generated by the element x to the power n over d is going to have order d. Now the third and most non-trivial part of this statement is that if you have any subgroup of Cn with order d, then it has to be the subgroup generated by x to the n over d. Now, that's not to say that you won't be able to find other generators for this subgroup, but the point is that if you find two subgroups of order d inside of Cn, then they actually have to be the same group. At this point, I'd like to go through the proofs of each one of these statements to make sure that we fully understand them. The proofs of the first two statements are going to seem really easy because of the machinery that we've built up at this point. So for example, number 1 follows directly from Lagrange's theorem in the previous video. If you have a subgroup of a group, then the order of the subgroup has to divide the order of the group. That's the statement of Lagrange's theorem, and we proved it in the previous videos, so even though we could prove this other ways, we might as well use it here. The proof of 2 is also pretty straightforward. So first of all, by the theorem at the beginning that we called theorem 0, the order of the cyclic subgroup generated by x to the n over d is the same as the order of the element x to the n over d. And we proved earlier in the video that the order of x to the n over d in the cyclic group of order n is n divided by the GCD of n over d and n. Well, n over d is actually a divisor of n, so the GCD of n over d and n is just n over d. And when I work out what this is, I get that it's equal to d. which is exactly what I was trying to prove. So that establishes that for every positive divisor d of n, the subgroup generated by x to the n over d is a subgroup of order d. To prove property 3, we're going to use theorem 1. So first of all, if d is 1, then it's clear that h is the trivial subgroup, which is the same as the subgroup generated by x to the n, which is the identity in this case. On the other hand, if d is greater than 1, then we can let k be the smallest positive integer with the property that x to the k is an element of h, so that by theorem 1, h is generated by the element x to the k. Well then, by theorem 0 again, we know that the order of the group h is the same as the order of the element x to the k. And since the order of h is d by assumption, and the order of x to the k is n divided by the GCD of k and n, rearranging the equation here tells us that the GCD of k and n is n over d. In particular, that means that n over d is a divisor of k, which is the same as saying that k is a multiple of n over d, and which guarantees that x to the k is an element of the group generated by x to the n over d. Now if x to the k is an element of the group generated by x to the n over d, and if h is generated by x to the k, then that implies that all of h must be a subset of the group generated by x to the n over d. But these are two finite sets with order d, so if one is a subset of the other, then it means that they actually have to be the same. That establishes that any group of order d must be equal to the group generated by x to the n over d, and it completes our characterization of the collection of all subgroups of a finite cyclic group. I'd like to conclude this video by using what we've learned to draw the lattices of subgroups of a few cyclic groups. So for the first example, if p is a prime number, and Cp is the cyclic group of order p, then since the only positive divisors of p are 1 and p, the lattice of subgroups consists only of the trivial group and the whole group. So this is the simplest possible case. For a slightly more interesting example, let's draw the lattice of subgroups of the cyclic group of order 12. We know that there's going to be one subgroup of this group for every positive divisor of 12. So first of all, we'd like to determine the list of all possible divisors of 12. Well, 12 factors as 2 squared times 3 to the first. And by the fundamental theorem of arithmetic, we can deduce from this that the positive divisors of 12 are precisely the collection of all numbers of the form 2 to the a times 3 to the b, where a runs from 0 up to 2, and b runs from 0 up to 1. Now there are 3 choices for the integer a and 2 choices for the integer b, and any different choice for either one of these integers will result in a different divisor, so the total number of divisors of 12 is 6. Of course, this is such a small number that if you just brute force check all the numbers from 1 to 12, you probably would have found all the divisors by now. But I'm trying to show you a method that will work even for more complicated numbers. Well, anyway, going through all possible choices of the pair AB, we get all 6 positive divisors of 12, and I've listed them here in increasing order. Each one of these 6 divisors corresponds to a unique subgroup of that order, and if my original group is the group generated by x, then the subgroup corresponding to each divisor d is going to be the subgroup generated by 12 over d. So for example, the subgroup of order 12 is the subgroup generated by x to the power 12 over 12, or x to the 1, and of course that's the whole group. And the subgroup of order 6 is the subgroup generated by x to the power 12 over 6, or x squared, which is isomorphic to a cyclic group of order 6. Similarly, when I go through all the other possible subgroups, I end up with a lattice of subgroups that looks like this. And one thing to notice about the containments here is that a subgroup generated by x to the k, say, will be contained in a subgroup generated by x to the l, if and only if l divides k. So, going through all the possibilities shows that this is the lattice of subgroups of a cyclic group of order 12. For our final example, let's try to draw the lattice of subgroups for an infinite cyclic group generated by an element x. We know that every subgroup of this group looks like the group generated by x to the k for some non-negative integer k, and that all of those subgroups are distinct. So let's try to go through the possibilities. First of all, way down here at the bottom of the lattice of subgroups is the subgroup generated by x to the 0, which is just the trivial group. And on the other hand, way up here at the top of the lattice of subgroups is the subgroup generated by x to the 1, which is the whole group. Now there's also the subgroup generated by x squared, which is also an infinite cyclic group, but which is a proper subgroup of the subgroup generated by x. And then there's the subgroup generated by x cubed, and then there's the subgroup generated by x to the 4th. Notice that the subgroup generated by x to the fourth is also a subgroup of the subgroup generated by x squared. So we've drawn this vertical line here to indicate that. Now continuing in this way, we have the subgroup generated by x to the fifth, and the subgroup generated by x to the sixth, which is a subgroup of both the subgroup generated by x squared and the subgroup generated by x cubed. And then the subgroup generated by x to the seventh, by x to the eighth, by x to the ninth, by x to the 10th, and so on. Now, of course, I can't draw the complete lattice of subgroups here because there are infinitely many distinct subgroups of this group. But the important thing to pay attention to here is that there's exactly one subgroup for every possible non-negative integer power of x, and that the subgroup generated by x to the k is a subgroup of the subgroup generated by x to the l, if and only if L is a divisor of K. So that's a general sketch of what the lattice of subgroups of an infinite cyclic group looks like. Okay, well, that's the end of this video, and that's just about everything that you need to know about cyclic groups. In the next video, we're going to start talking about symmetric groups.